So here we go, the final section of the higher level kinetics topic. We're pretty much bang on where I would expect to be at this time of the year. The one thing missing obviously is having done some practical work, but those will be relatively straightforward and easy to catch up. So what are we looking at? Well, in this section we're looking at activation energy and how to determine the activation energy. We should all know that the activation energy is the minimum energy to start a reaction, or the minimum energy required for a successful collision, etc. But minimum is a key word there. And what we're going to find out is how to determine the activation energy for a reaction from experimental data. This is something that you might like to do for an IA. So, something odd with the sequencing there, but the rate constant, K, increases exponentially with the temperature according to what's called the Arrhenius equation. And there it is. A is called the Arrhenius constant. He named it after himself, very modest of him. And it's related to, still some strange sequencing going on here, the orientation of the reactants when they collide. EA, activation energy, we've seen that before. R, universal gas constant, you've seen that before as well. And T is the temperature in kelvins. And this little number here is a constant. It's the number upon which natural logs are based. Normal logs are based on base 10. Natural logs are based on this number E. Now that equation is given in the data book, so you don't need to learn it, but make sure you know what the various things are in it. Now, more often, that equation is actually expressed in a rather different form. Those who are good at maths will know if you take natural logs of both sides of that equation, that is what you end up with. So, now, if you're a good mathematician, you'll straight away spot something. That is in the form y equals mx plus c. Yeah, that was obvious, wasn't it? So, we can do some graph plotting. And if we plot natural log, excuse me, natural log of the rate constant against 1 over the temperature in kelvins, we will get a straight line. That straight line will have a gradient of minus EA over R. So to find the activation energy from the gradient, we just need to multiply by minus R, minus 8.314. The intercept on the y-axis is natural log of A, the Arrhenius constant. Now, be careful when you are multiplying by minus R, the value you get for the activation energy is in joules per mole. You always need to quote it in kilojoules per mole. And if it comes out with a negative value, I'm afraid you've messed up somewhere. There are some examples on a worksheet which I've attached to this. They will take you some time to do. It takes a while to fiddle around and actually work out natural log K and 1 over T before you go on to plot them. I'll get you just to do a couple of the examples and then I'll share my answers with you. It's quite tricky to do without graph paper, but it is doable on a spreadsheet. If you use Google Sheets, it's doable. The one thing you're missing out on obviously is practice at plotting a graph. It's also, I believe, doable on your graphical calculator. But I haven't a clue how you'd actually do that. Now, there are a couple of problems on there that you need to solve using this equation. Yes, oh my goodness. Don't learn that equation. It is given in your data book, and it simply wouldn't come up in the multiple choice exam. So that's for questions 5 and 6. You'll have a variety of different numbers. Well, have a look at the questions and see what you've got to do, and you'll need to do some rearranging of that formula to help you do it. So a little bit of maths there, I'm afraid to say. Okay, there we've got K1 is the rate constant at temperature 1, K2 the rate constant at temperature 2. And it doesn't matter which way round you have as T1 and T2, as long as you're consistent with the formula. So that is the end of this section. Okay, I've now got to make a decision as to what we do next. It will almost certainly be organic chemistry. That's what I would normally do now. So be prepared for having a look at topic 10 next week, because I'm not going to set you too much more on this. This little worksheet will keep you quiet for quite a long time.